Imagine a fighter jet, heavy with fuel and ordnance, needing a runway 3,000 feet long to lift off. Now picture that same jet on a ship's deck, just 300 feet of steel, surrounded by ocean. It seems impossible, but this is precisely what aircraft carriers do every day, using a hidden technology that hurls the plane into the air in under 2 seconds. This is wings and wrecks, how machines fail, and what saves the people inside them. The secret is the catapult, a powerful machine hidden beneath the deck. As the US Navy training manual states, the catapult is the most powerful piece of machinery on the ship. It can throw a 45,000-pound airplane from 0 to 150 miles per hour in less than 2 seconds. That force, generated by steam from the ship's nuclear reactors, turns a short deck into a launching pad. So how does this work? When the pilot gives the signal, a blast of high-pressure steam drives a piston along a slot in the deck, pulling the jet forward with immense force. In less than 2 seconds, the aircraft goes from a standstill to flying speed, and the myth of needing a mile-long runway is shattered forever. But where does that steam come from? The answer lies deep in the ship's hull, where nuclear reactors generate steam at 600 pounds per square inch. That steam doesn't just power the ship, it fires the catapults. When the launch officer triggers the catapult, high-pressure steam rushes into a cylinder beneath the deck, driving a piston forward. That piston is attached to the jet via a shuttle, yanking it from standstill to 150 knots in under 2 seconds. The US Navy training manual sums it up. The catapult can throw a 45,000-pound airplane from 0 to 150 miles per hour in less than 2 seconds. This repeated emphasis underscores the sheer force at work. But this brute force comes at a cost. Steam catapults require constant maintenance. Their seals leak, and pressure drops after each launch. That's why the crew must wait nearly 30 seconds between shots, recharging the system for the next jet. What does a catapult launch feel like? In under 2 seconds, a 45,000-pound jet goes from a dead stop to 150 knots. The pilot is slammed back into the seat by 4 to 5 Gs, a force that would leave most people unconscious. One pilot described the moment of launch as like being hit by a truck. The G-forces push you deep into the seat, and you have to fight to keep your wits. Any lapse in control could send the jet into the sea. These extreme forces are the price of launching a fighter from a deck only 300 feet long. The catapult's steam pistons deliver a controlled explosion of power, accelerating the jet faster than a dragster. It's a violent, precise, and utterly necessary act of engineering. Why did the Navy seek a replacement for steam catapults? Because steam systems have limits. They can't launch lightweight drones, and their violent jolt stresses airframes. The answer is EMALS, the Electromagnetic Aircraft Launch System, which uses linear induction motors for a smoother, more versatile launch. Instead of steam and pistons, EMALS uses linear induction motors, essentially a giant electromagnetic track that accelerates the shuttle smoothly. This means the force on the aircraft can be precisely controlled, reducing stress on the airframe and allowing launches of both heavy fighters and lightweight drones. The Naval Air Systems Command explains the advantage. EMALS provides a smoother acceleration profile, reducing stress on the airframe and allowing for a wider range of aircraft to be launched. That includes drones, which steam catapults could never handle. But the real revolution is in the numbers. The USS Gerald R. Ford, with 4 EMALS catapults, can launch 160 aircraft per day, over 50% more than a Nimitz-class carrier with steam. And with fewer maintenance crew, the Ford class needs 400 fewer sailors. That's the future of carrier aviation. So the catapult hurls jets off the bow. But how does a carrier recover them without a mile-long runway? The answer came in the 1950s. The angled deck, offset 9 degrees from the ship's centerline. It allows simultaneous launch and recovery, turning the deck into a 2-lane highway. Before the angled deck, a landing jet that missed the arresting wires would plow into aircraft parked on the bow. The new design lets pilots abort and throttle up for a second try. Naval historian Norman Friedman called it the single most important innovation in carrier aviation since the jet engine. Now the carrier can launch and recover jets in a continuous cycle, a 30-second launch, a 400-foot landing. The angled deck doesn't just add safety, it multiplies the ship's striking power. And that's how a 300-foot deck projects force across the globe. How does a 50,000-pound jet landing at 150 miles per hour stop in just 400 feet? The answer lies in the arresting wires, 4 steel cables stretched across the deck, each connected to a hydraulic engine that absorbs the aircraft's kinetic energy. Stretched across the deck are 4 steel cables, each connected to a hydraulic engine below. As the jet's tailhook snags a wire, the system absorbs its kinetic energy, converting it into heat and pressure, slowing the aircraft with controlled, relentless force. The US Navy fact sheet states, "The arresting gear system can stop a 50,000-pound aircraft travelling at 150 knots in just 400 feet. That's the same force as a car crash, but engineered to happen safely, every single time." So why does a 30-second launch cycle require such tightly choreographed ballet? Because on a carrier deck, every second counts, and every mistake can be fatal. The deck crew, each wearing a colour-coded jersey, moves with precision, honed by thousands of repetitions. The yellow-shirted launch officer gives the final hand signal. The catapult fires, and in less than 3 seconds, a 45,000-pound jet accelerates from 0 to 150 knots. The crew has already reset the catapult for the next aircraft, all within that 30-second window. But this dance is performed on a crowded deck with jet exhaust, spinning propellers, and moving aircraft. A single misstep can be catastrophic. That's why every crew member trains for months, memorizing their role until it becomes instinct. So the catapult and the angled flight deck and the arresting wires work together in a seamless cycle. A 30-second launch, a 400-foot landing. And that cycle, repeated hour after hour, is what allows a single carrier to project the air power of an entire air force anywhere in the world. But the real marvel's not just the machines. It's the 5,000 sailors who orchestrate this ballet in the middle of the ocean. Every launch is a controlled explosion of engineering and human precision, turning a 300-foot deck into the most powerful runway on Earth. But how does that steam actually move the piston? Inside the catapult cylinder, a series of valves open in sequence, admitting steam behind the piston at precisely timed intervals. This creates a smooth, continuous acceleration, not a single violent shove, allowing the jet to reach takeoff speed without tearing itself apart. But the catapult doesn't fire itself. A yellow-shirted launch officer stands on the deck, watching the jet and the steam pressure gauges. With a final hand signal, a dramatic point toward the bow, he triggers the launch. That split-second decision coordinates the entire system, ensuring the jet is ready and the deck is clear. Before launch, the jet is held in place by a holdback bar, a mechanical fuse that releases at a precise tension. As steam pressure builds, the jet strains against the bar. When the force reaches the right level, the bar snaps open and the shuttle yanks the jet forward. It's a controlled release of stored energy. After the catapult fires, the spent steam is vented into the atmosphere through vents along the deck. That dramatic cloud of steam you see in videos is the system resetting. Meanwhile, the piston is retracted back into the cylinder by a retraction engine, ready for the next jet. The cycle repeats every 30 seconds. But steam has its limits. EMALS, on the other hand, can launch a lightweight drone with a gentle acceleration, then immediately launch a heavy fighter with full force. The system's computer adjusts the power profile for each aircraft, reducing stress on the airframe and expanding the types of aircraft a carrier can operate. And the angled flight deck doesn't just allow safe landings, it also enables rapid deck cycling. While one jet is being launched from the bow catapults, another can be landing on the angled deck aft. This simultaneous operation doubles the sortie rate, allowing a carrier to strike multiple targets in quick succession. When the jet lands, its tailhook snags one of 4 arresting wires. The wire is connected to a hydraulic ram that absorbs the energy. As the ram extends, it forces hydraulic fluid through a series of valves, dissipating the kinetic energy as heat. The aircraft stops in just 400 feet, and the wire is reset in seconds. But all this machinery is useless without the deck crew. Each colour-coded jersey has a specific job. Blue shirts move aircraft, red shirts handle ordnance, green shirts operate catapults. They train for months to execute their roles with split-second timing. A single mistake can cost lives, so precision is everything. And that's the answer to the riddle. A carrier doesn't need a mile-long runway because it carries its own launch and recovery systems. The 300-foot deck is not a limitation, it's a weapon. And every time a jet screams off the bow, it's a testament to the ingenuity that turned a short deck into global power.
Every failure leaves a lesson. Subscribe so you don't miss the next investigation, our next video.